This is about interpretation. And this is continuing from yesterday. We talked about how the ether was originally postulated specifically because a wave needs a medium to be able to exist. Because the idea of a wave is that it's an action, it is something that occurs to something else. Now, let's see, today we're going to move forward from there and look at, and just capping off what yesterday, the end result of yesterday was specifically to say that there is, Einstein's theory of relativity was originally, it came from, its predecessor was Lorentz ether theory, and Lorentz ether theory, the mathematics for it, were a mathematical description of exactly how ether affected light. So the change factor, the mathematics for that was designed around the way in which a moving medium impacts light, and that is what that calculation was for. So the idea that there is a relativistic ether, and that can completely conform to all of the ideas of time dilation, length contraction, and effects like those. All of those things can be seen in an ether environment. So today what we're going to talk about is that fluid dynamics and quantum mechanics are completely interchangeable. And this is something that's not very well known. So I want to read a couple of quotes to start off. Anyone who is not shocked by quantum theory has not understood a single word, Niels Bohr. If you're not completely confused by quantum mechanics, you do not understand it, John Wheeler. Quantum mechanics makes absolutely no sense, Roger Penrose. And it is safe to say that nobody understands quantum mechanics, Richard Feynman. It's good making use of the clicker thing. And, all right, so this one, I've got a lot of quotes. You guys are going to have to bear with me as I just run through quotes, because I like those. So the duty of a man who investigates the writings of scientists, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. He should also suspect himself as he performs his critical examination of it, so that he may avoid falling into either prejudice or leniency. I don't know how to pronounce his name, but you guys can read it. Science is the belief in the ignorance of experts. Once again, Richard Feynman. And unthinking respect for authority is the greatest enemy of truth, Albert Einstein. So, one of the things that is very well known about quantum mechanics is the idea of wave-particle duality. And whenever you start getting into wave-particle duality, you start asking questions when you're younger or you're first interacting with it, and you're like, well, is it both wave and a particle? You go, no. And so it's both a wave and a particle simultaneously. So does that mean that there are particles waving? Because yesterday we showed how waves actually impact the particles, the way that the medium's moving around. No, that's not it either. Which is why those quotes earlier, it is safe to say that nobody understands quantum mechanics. It's because the idea that they were getting around it, you could not come at it from any perspective that makes sense to a person who's thinking in a mechanical fashion. However, in light of recent evidence, which we'll be going over today, that's no longer true. There is a way in which you can conceive of both a particle and a wave, and of them working together, and there are experiments which show that. So the idea is, do we need it? In 1926, just 1 year after the formulation of Schrödinger's equation, when you're talking about the basis of quantum mechanics, it's going to go back to Schrödinger. Ernst Madelung demonstrated that it can be recast in hydrodynamic form. So this is basically saying that there is a fluid dynamics version of quantum mechanics. Now, here we're talking about particles, but they can be treated in a completely through fluid dynamics. And that's the thing that I want to get across to you today that most people really don't know. So by 1950, the phase-space formulation of quantum mechanics provided a fully realized and valid formulation of the science which could deal with both position and momentum in a classical manner. The Wigner-Weil transform provides a mapping between the formulations of quantum mechanics and Hilbert space operators, and I'm not going to get too much into that. So just the point is here that there is, this is actually an excerpt from a paper I wrote, and so it's getting a little too technical. The point is that there is a way of mathematically treating quantum mechanics through fluid dynamics. Now this seems weird, right? Because if it's particles, then how can you treat it entirely as a fluid? Because there are ways in which we use conceptions that are useful, but are not really accurate to what's going on underneath the covers in reality. Like we talk about gallons, in the pool, but are there really something called gallons in the pools? Not really. So basically, yeah, the TLDR, it's just waves and fluid motions can accomplish all of the same things as current particle physics, as quantum mechanics. So then why do we have this wave particle duality? Where does this all come from? I showed yesterday how if I were to shoot a bunch of marshmallows at a thing here, I could have those two lines. But then what we did is we're believing that it's made out of particles, and then we fired them at this two slits, and what comes out the other side is not the way the particles behave. But it's also kind of the way the particles behave, because what happens is that as we fire it through there, we actually fire enough energy for it to be just one electron, is what we call it, or one particle. Actually, the first one was done with light early on, but it was with very, very minimal amounts of light, so that they figured that there was just the amount of light that is equivalent to a single particle. So they go through and they actually, one at a time, you see that picture that's being built up there, can be built up one at a time. So how can it be, we know that there's some waves going through each side and then be interfering with each other. If you only send one at a time, how's it interfering with itself? It's nonsensical. And then from that nonsense, we kind of had to spin off into crazy land to try to figure out any way in which we could grasp it, and that's why there was something called the shut up and calculate, idea behind quantum mechanics. So let's see, another Feynman quote. We choose to examine a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in the heart of quantum mechanics. In reality, it contains the only mystery. We cannot explain explain the mystery in the sense of explaining how it works. We will tell you how it works, and in telling you how it works, we have told you about the basic peculiarities of all quantum mechanics. So this is really the basis of what everything that's weird that you've heard about in quantum mechanics, everything from entanglement, you name it. It kind of comes down to this. This is the point at which we said, okay, stuff got weird. And I'm pointing this out to you that he said there's no way to explain it. Now that's because he did not have the Coudet experiments, which have come about in the past 10 years or so. And now there is a completely mechanical, intuitive way to explain the reason why we came up with all the crazy explanations. The whole reason why we came up with them is because this didn't make sense. It now makes sense, so we need to go back and fundamentally doubt all of the things that spun off from here. If here we thought there was absolutely no way to explain it, but there is, now, since there is a way to explain it, we need to look at everything from that point forward with doubt. That's something that is very difficult to do because you're talking about revolution. Look forward. That's the problem with this program. It really hates GIFs and anything that's doing any kind of video. It bogs down the computer for some reason, which just makes no sense. They just got it really bad. Oh, there went three places. Thank you. I wanted to go 3 places. Definitely. Okay, so uncertainty. You're probably feeling it right now. There's something called the uncertainty principle, which is that. So from that point, we had this idea that you can that it's both a particle and a wave. And second, so how do we deal with the fact that a particle is like spread out over an area? In other words, whenever we want to know its momentum, the better we know its momentum, the worse we know its location. And the better we know its location, the worse we know its momentum. And however, now people don't like this analogy, but this is the analogy that best works, and it's one that I think Schrödinger would agree with as well. You can see in these different photographs, what's occurring here is you got a smeared out ball. Why is it smeared out? Because as the camera shutter opens, there's a period of time it opens before it closes again. And so the shutter speed determines how blurry a moving object is. Now, if I know how fast the shutter is open and closed, then using that, I can actually determine the distance that ball traveled in that time by looking at the whole area in which it's smeared out over. Now, so the thing is, I cannot determine, see the one right there in the very middle, I can't determine how fast that thing is going.
because it's not smeared at all, because I've determined its location very, very well. But then, these ones that are more smeared out, I can determine their momentum, how fast they're going. I'm using analogies here. You can see how fast it's going simply because it's smeared out more. And the more it's smeared out, the better I'm going to be able to get its actual speed. So there is the quality of these two things are not as magical seeming as they might seem. It's a part of how the math is mapped to reality that it's a little difficult to understand until you have some analogy like that. And that's what we have in quantum mechanics, this inability, this uncertainty principle. Now, a number of there was things that happened. Let me see my next one here. Okay. So there were a number of things that happened with the Copenhagen interpretation. There are 3 interpretations. Only 2 of them have been popular up until the past 10 years, and that is Copenhagen in many worlds. But there is a third called de Broglie-Bohm, or pilot wave theory, and that was brought out, and now that is resurfacing. That's the one I'm going to talk about the most. But for a moment, let's talk about the Copenhagen. Copenhagen is the one where everything magical that you've ever heard about quantum mechanics comes out of Copenhagen. If you've heard that it does these things that are nonsensical and you can, anything wild that you can think of with quantum mechanics comes from the Copenhagen interpretation. And all the ones where you start hearing about these spiritual interpretations of whether or not a person is consciously focused on something determines whether it's there or not. These things all come from the Copenhagen interpretation going off in one direction and going off in another direction, and different people's take on what that has to mean. So the Copenhagen interpretation is that this idea of probability, and there's a certain probability you're going to find the particle within the whole area that you are basically taking a picture of, and it's not really reliable like the ball is. The ball is just going straight. Whereas whenever you're trying to find a particle within its probability area, it could be anywhere in that whole area within a certain, given probability. Copenhagen interpretation says that's bottom level. It's not that there are a bunch of events that you're checking out that are probable. No, probability is the bottom layer of reality. And that is where you kind of have especially if you become a programmer or anything like that, the idea of random is one of those things that's useful but doesn't exist in reality, like the number 0. 0 is extremely useful. It's necessary even, but it is not something that exists really in reality. And so the same thing can be true of probability. Probability is a description of something that is a useful tool for us, but it is a human idea of how things work out. It's how we deal with what seems to be a random world. Now, with many worlds, you know what? I think I got some slides. Copenhagen has the spooky action at a distance thing that Einstein didn't like, which is your entanglement, which I'll explain a little bit more later. Many worlds is theoretically deterministic because the fact that all the worlds, like at any moment that anything changes in a particle, worlds split off from it. And all of them are real. And so therefore you can see how it is. There's not some underlying mechanic that's kind of spooky, requires a person to be focusing on it or anything like that. It splits off into lots of. So there's certain people who, because they like determinism better, they actually prefer many worlds. And you'll see there's a schism among very reputable scientists on whether they like Copenhagen or many worlds and the reasoning for why it is that they like each one of them. Now, de Broglie-Bohm, I hate that. So whatever you're trying to spell, you have these mnemonics. So I end up I'm always hearing it as de Broglie instead of de Broglie. I think, by the way, there's a requirement if you're going to be a physicist that you have to have a difficult to pronounce name that doesn't match how it's spelled. I think that's in the book somewhere. I'm pretty sure. And these names I put down here at the bottom, these are some of the researchers that are working on de Broglie-Bohm right now. And it's John Bush at MIT and Ross Anderson at Cambridge. And actually kind of keep in contact with Ross. All right, so going over to Copenhagen. Yeah, this is good. So the idea is that you've got this wave function. Basically, that is just a mathematical description of a wave that can do things in Copenhagen. And that is when you can see the probability and then the position is spread out, where the particle might be in depth, and when it's there. When it's there, that's what after the wave function collapse. And that is after anything that makes it where you can determine where the particle is, they say, well, the wave function has collapsed. And this event is caused by, instead of, and you're like, oh, well, it's the observer effect. You have to, throw a particle at it and touch it or something. You have to interact with it in some way, and that's why it's collapsing, right? They go, no. You go, what? What? And so, and the funny thing is, in recent times, they've actually been melding more towards, well, yeah, maybe it is just because you have to hit it with a particle to observe it. And you watch this happen over history. It's kind of funny. But, so, over here on the right, what I have is Schrodinger's cat. Everybody should kind of be familiar with it. And the funny thing is, it's since like the 1950s onward, Schrodinger's cat was actually used as like a teaching tool. That's when they're first introducing it to you. It's like, yeah, this is how quantum mechanics works. It was Schrodinger's ridicule, is what it was. He was ridiculing people for having that idea of reality. And this is his quote about it. And that is, one can even set up quite ridiculous cases. But hold on, let me go ahead and explain it real quick for anybody who's not familiar. Basically, just you can have a probabilistic event such as the decay of something, so radioactive decay, which then, if it's a 50% probability, once it reaches that, if you haven't observed the cat in the box, then theoretically, his life or death, whether or not it releases poisonous gas. Whether or not it releases that poisonous gas is a 50-50 probability. So right now, because you've not observed the event of the decay of the atom, and the decay of the atom is what causes the event, then the cat is 50% alive and dead if we believe that things can exist in a 50-50 position like that, what they call a superposition. So you have to believe that that is also true. And that's why he was talking about this, because you can even set up ridiculous cases. It is typical of these cases that indeterminacy originally restrained to the atomic domain becomes transformed into macroscopic indeterminacy, which can then be resolved by direct observation. That prevents us from so naively accepting as validate the Word model for representing reality. In itself, it would not embody anything unclear or contradictory. There is a difference between taking a shaky or out-of-focus photograph and a snapshot of clouds and fog banks. So here was something that he was using to ridicule people and tell them that they were off their rocker. This is ridiculous. I'm the one who even designed this, the mathematics behind this. What are you people doing? What are you thinking? And instead, for years, we've been using this as a way of teaching people the awesome power of this nonsensical idea. And it's at this point that people go, well, if waves can exist without a medium, why not allow probability to exist without events? It's just probability. It's pure by itself. So you can see how basically there are these 2 points at which this is all about metaphysics. The mathematics do not change. They're still useful. They still describe the same things, but you can look at it in a completely different way and get something completely different out of it. So here's a description of many worlds. Basically, here you have after the Schrodinger's cat. You can see on one side it splits off in the world where the cat's dead. The other side it splits off where it's alive. And in any event, starting all the way from the Big Bang, and that any event being any interaction of particles, splits off. And so you're talking about in a single moment, based on one atom in my fingernail, billions of worlds were just created. And so and so if you try to track this from the level of infinite we're talking about is absurd. I forget that there's these different kinds of infinite, uncountably infinite, I don't know. But the point is, I'm trying to show you how crazy the idea is of how many worlds are being created at every moment based upon the many worlds interpretation. So, and I like to include a little funny slide every once in a while. You're not just wrong, you're wrong at every conceivable scale of resolution. Zooming in on any part of your worldview finds beliefs exactly as wrong as your entire worldview. So sometimes that's how I kind of pick up. It's just something silly. So Which, of course, I'm sure that people like to say the same of me. It's one of the fun things in looking at interpretations of evidence. So, with particles and waves, I want to blur the line of particles and waves for you for a moment, in preparation for focusing back on how these two concepts can go together. So, there are these things called phonons. Okay, now everybody's probably familiar with the term photons. It's a particle of light. However, there's also something called a phonon. And basically what that is a quantum mechanical treatment of mechanical waves in a medium. So even though there are particles already there, when they talk about phonons moving around in this medium, they can be talking about a crystal, something that's solid. And they're talking about the waves, which are conventional mechanical waves, in the same way that we talk about mechanical waves. And those waves can be treated in the same way as we treat other particles in quantum mechanics. And that is basically there are real ways in which they have these behaviors that act like quantum mechanical particles. And so there are these particles. It's a particular treatment. It's a way to divide up the energy of the waves. So since photons are something that behave in a certain way, and we've been saying, well, maybe it's actually we got fluid mechanics here that can entirely treat it. Then there's not necessarily a reason to believe that photons are any more really discrete than phonons are, because it's basically the same thing. We're treating it as particles, but it's not necessarily a real physical thing that exists per se. So the question is, are we mistaking a property for a physical quality? And that's why I want to ask, where's the border of a tornado? Think of a tornado. The moment you think of a tornado, you almost always will think of the borderline of the cloud. However, immediately you can realize, well, does damage happen around the cloud? Of course. It's not just that edge of the cloud. So therefore, the tornado is actually bigger and doing damage. And in fact, that borderline represents something almost entirely arbitrary, but it's tied to something real. And what that borderline is it's tied to a physical property of reality, and that is relative humidity. As the cyclone is spinning, what is happening is that you are changing the density of the air. Well, the speed of the motion of the gases are changing the density of the air, and that alters the relative humidity such that there is a borderline where the relative humidity allows droplets to form in the air, and it creates a cloud in the area that's the edge of the tornado. And just beyond that, you've passed the borderline of where those droplets will go from a gas to a liquid. So you've tied this borderline, you've abstracted it, you immediately think of this borderline, but is it really real? Is the tornado right there? Is it that one thing? Or is it actually just the focal point of the energies of the entire storm? And understanding that it is simply a focal point of the energies of the storm, and your idea of borders in general is actually something that it's a tool that you need as a human to communicate with yourself, to conceive of things, but it is not necessarily really a real border. It's just connected to things. It's an abstraction that you use. So, one of the examples I give is this is a unit of transition. If I were to take the heat energy required to heat 1 mole of water from frozen to boiling, I can call it a shrew, whatever. And then I can talk about how many shrews are in this water here when it, did some sort of behavior. And it would kind of make sense to a certain extent because you'd see physical transitions that would happen to the water. It would actually become boiling in one area and not in another. And so it would give reality to these units that are not really real per se. So there are multiple explanations for the the dual slit experiment. And in this one, what I'm going to give you is a way that it can actually be explained. And that is, say I had a bunch of moai or whatever, and I submerged them halfway in the ocean. So they're half submerged. And then waves came up against the moai, and they're all in a line. Well, what's going to happen is it's just going to reflect that energy, and none of them are going to get knocked over at all. However, if they were configured the right way, they could capture the energy that is spread out across this wave, and the wave would build up, and the amplitude would get larger and larger and larger and larger, and finally knock over the one at the very back. And so there is an amount of energy that has to do with an interaction here. And that interaction can be based on one particle. Remember how I was saying there was just one particle on a screen that was appearing whenever they fired waves at it, and somehow, it's like we're seeing one electron. However, is that electron real, or is it this? Because this animation should still be going, but basically the surface of anything down at the very small level is just flipping out. It's like a mountain range that's going all over the place. And so there is a randomness that is already inherent, which we can get back to it later why that's there, Brownian motion. But so it's moving all over the place. So there's good reason to believe that perhaps this is the way in which it's creating that single particle. You're sending out the energy to allow one particle to interact with one atom, to knock it over, to spin it up, to whatever that you want to say. But perhaps it's still, it has to do with transition. So no need to be discrete. So here is something called the Coudet experiments. Now remember I promised you that there was a recent experimentation. What we do is we have all of the various spooky and interesting and weird actions that occur at the quantum level. And what used to be, we'd always say, is confined to the quantum level. You cannot see it at the macro level. That is no longer true. What is now true is that what we did is we take, Yves Coudet took a droplet of silicon and put it on a bath that is already vibrating to some small extent. And so it is a silicon, it's a bunch of just silicon liquid. And when you make the droplet the right size, it'll bounce on the surface indefinitely. It'll continue to bounce. And it creates waves around itself. And it then interacts with the waves that it creates. And in so doing, what it does is there is I don't know if anyone here is familiar with chaotic determinism, but the idea is that there are systems which are so complex that while they are truly deterministic, there are too many small effects added together to be able to really you can't even mathematically get there because you can't get enough information about it. It's just the information is not available. So it might as well be random to you for all intents and purposes, most of the time. However, it is not actually factually random. I'll let you guys read and watch this for a moment. This is interesting. Okay, just in case you weren't able to read it, because I did have that at like max speed. Basically what it's saying is that as the droplet moves around in its corral, it describes its likelihood of finding it. In other words, the period of time it spends in any one location. The likelihood of finding it in any one location is a probability wave. And it matches our, specifically the statistical behavior described as the Schrodinger equation. In other words, the moving of that single particle bouncing with its wave actually matches quantum mechanics. And it does so in a variety of ways. So it's basically, it is a particle riding a wave. So let me go to the next slide here because I do have a little more explanation. Oh, it's gonna take forever to go to the next slide, isn't it? It doesn't like me. So let me just continue on without it. The things that you'll see is that the double slit experiment has been performed where you have a single particle that's bouncing. What you see is the wave that it creates actually travels through both of the slits and then interferes with the other side, which then determines a path for the bouncing droplet that matches, the interference pattern that we see whenever we have the single particle two-slit experiment. So you get the same effect because the particle will strike the distant surface with that same probability pattern that we have seen. So all of those weird effects that Feynman was saying you cannot describe we now describe. In addition to that, there's something called quantum tunneling. We also see this effect in where they did is they created a border by making it where the waves could not easily traverse a very shallow area. And so, but then on occasion, with roughly the same probability that you would see with quantum tunneling, the particle would have enough momentum to overcome the distance and actually make it out of this artificial, corral that is blocking some of the waves transmission. So, so you have every single one of the effects that you might see in. What is going on here? Come on. All right. Leave this. I should have just done that in the first place. I didn't know that would be so fast. Okay, there we go. So there it is, traveling through the two things, and no, wrong one. All right, I'm gonna get this. Bear with me.
That's what they said at the news camp. Please bear with us.
Oh, there we go. All right, and this is a quote from a paper from the fellow I mentioned, Ross Henderson at Cambridge. And it is Maxwell's fluid model of magnetism shows that a wave packet traveling along a phase vortex in a Eulerian fluid obeys Maxwell's equations, is emitted and absorbed discretely, and can have a linear or circular polarization. What's more, the measured correlation between the polarization of two co-generated wave packets is exactly the same as predicted by quantum mechanics and observed in Bell tests. Basically what he's saying is that whole spooky action at a distance thing can be explained with fluid mechanics, and it's no longer spooky, it's completely deterministic and something that doesn't have that weirdness to it. And so that's what he's saying. What I was showing you here on the right, by the way, was a single droplet. You saw it moving with particles in it. Let me see if I can get it to, I'm going to escape and restart it this way, because it seems like it likes to do it this way. So the one I'm showing you here on the side, what you'll notice is the fluid motions are complex. Like you've got a vortex in this direction, and then you've got a counter vortex in this direction. And there's something called wave-vortex duality that's kind of well known in fluid mechanics, and that is when you have a standing wave, you also have vortices that accompany you. And they're, well, without getting too much into stuff that I don't know that well, the point is that there are these shapes that can come out of simply bouncing a droplet of water at the right frequency and amplitude. You can actually create these various what's it called? Crystalline-like shapes. So what I'm leading towards here, let's see if I can get to the next part. Here we go. Is an explanation of what might be occurring, and for an analogy to the. And this is kind of a lead up to tomorrow, by the way. What might be occurring as a three-dimensional analog to what you're seeing as a two-dimensional system with the dropping, the bouncing droplet. So here is a high-speed photography of a gun being shot underwater. And what you're seeing happening is not just the gases, which are here at the front, opening up and closing, but actual vacuum areas where there's a few particles of water in there that have been ripped off, but by and large, it's mostly vacuum that is ripping open and slamming back together and ripping back open again, because basically the sphere of energy turns around, comes back, and goes, and it turns itself inside out, basically. And so this cavitation effect is very interesting because there are a variety of things in looking at how this system might be playing out in a way that is analog to the Coupe experiment. Because, of course, what we were looking at was something that was driven by gravity, right? We had gravity that was the restoring force to make that droplet go up and down. So where would it be if you're talking about a three-dimensional system? This is one of the analogs that we have to examine the idea of a three-dimensional system that would have a restoring force, which is, of course, the pressure of the water. And it's something that might have that bouncing effect. So that's something we're going to talk about more tomorrow, which we're going to just go all the way into speculation land. Totally, tomorrow is Mad Science Day. We're going to get really speculative and talk about all the things that might be happening there. One of the interesting things you might have noticed just then, by the way, is that there's something called sonoluminescence. As the wave collapses, what will happen is it'll give off light. And so basically, you see that these things right here, those are not just artifacts. That's actually light being given off. It's called sonoluminescence. And so basically what's happening is it's converting mechanical energy into another kind of energy. It's taking something that is purely mechanical and then converting it into light. And so that's like basically it's kind of, it's just an energy conversion, and that's the important part I want to get across to you here and not go too far afield. Okay, this is called, and once again, I'm getting too much into it tomorrow. I probably should have cut this a little shorter. Is there any questions?
I noticed there was a discrepancy between the Schrodinger equation graph and the corral, where the Schrodinger graph had a higher probability on outside ring. Are you going to discuss that discrepancy at all?
I'm not going to get that much into it because I'm more of a historian of science than a scientist. And so I get into looking at what's happening in the trends and what professionals are doing and how. It's basically I'm trying to make science communication a little more technical, and I have written a paper in a philosophy journal that is basically about the philosophy. It's about the idea that the way that we look at things is very important. It's not something that we're doing in science very well because we tend to believe that math is reality, and when you don't understand that math is a tool for describing reality, then understand that there's an analogy. And that analogy can be broken, it starts to go away. And so that's sort of something that I've been trying to tackle and trying to we're actually going through a revolution right now in the social sciences world. It started there. Now it's starting to happen in biology as well. They're starting to recognize that the pressure of pharmaceutical companies and the urge to publish has caused a lot of problems with replicability. And a lot of that is tied in with these social factors, these ideas that we hold and we go forward with them. And it's not that these people are just greedy and just honest one. No, they're going on an idea that they had and just rushing forward from it. And so what happens there is you rely on your axioms, and sometimes your axioms are false. And that's the problem with axiomatic logic, is that you have to rely on something being true. And so it's part of the cycle of science. And so that's really more where I go. So some of the things, when we talk about very fine things, there's a lot of work that needs to be done here that we have barely touched. The idea that it's possible that there is this ether view is so revolutionary that most people don't even want to look into it. Like I was talking about Wes Anderson, I met him at Berkeley, and he actually is the computer, what is it called?
Security?
Yeah, security expert at Cambridge, and he was lecturing here, and he works with some of the physicists at Cambridge who are not theorists and various things like that, and they don't talk about this to everyone because there is such a huge pushback that you endanger yourself academically by talking about anything that is outside of the orthodoxy. Talking about things that are outside of orthodoxy is just a good way to cause yourself a lot of problems. And so, yeah, so that's I'm not going to be able to answer some of those questions.
The reason I asked was only because, if I remember correctly, the slide also said that the Schrodinger equations are a valid description of the process. They actually come to the correct observations.
Mm-hmm.
So when I saw the physical graph versus the calculation, which is supposed to, in the long run, have a similar picture of reality, right?
Mm-hmm.
And they don't actually.
Well, okay, let's take a look at it.
Yeah.
So you're,
and I guess not to get kind of hung up in minutiae.
Theory and practice are the same, and in practice they're not.
Yeah. Also, not to get too hung up in minutiae, are you implying that gravity is a third pressure?
Yes, I'm implying that there is an analogy between gravity and the pressure of a fluid, because dense space-time. So you missed yesterday's lecture, and understanding that that there is a relativistic ether that is absolutely crucial to being even slightly able to accept the idea that there may be a description of relativistic physics that is also fluid-based. So yeah, I will be putting that up online, and it is very important to understand the analog between them, where special relativity came from, so that you can understand how general relativity then came from there. So there's
There'll be
a variety of
a
things that's out
website
there,
launch
but-
in a few days that
Yes,
they can.
yeah.
Yeah.
So the analog between the Bernoulli's principle and gravity are something that is talked about in a few of Ross Anderson's papers. So I can give you some links to those. And so yeah, there is an analogy there that it has to do with pressure. And if you think about the way in which bent space-time works, it is a lot like a pressure gradient, basically. And for instance, if you were to take two tornadoes and you put them nearby each other, they are drawn to each other in a way that is very much like gravity, though we might also think of it as buoyancy, because it's basically two gradient fields of pressure that cause them to just, they're just simply seeking the area of least resistance that draws them together. So there is a lot of good reason to see that the alterations in fluid pressures would be something. But then, of course, you've got a lot of questions that should come from there about experimentation. What about this experiment? What about that experiment? What about that? That I'm actually putting in a book, and it is something I've done a tremendous amount of research on to say, okay, so how could this experiment work within this world? Because now you've got all these things that we've been applying this idea to how this must be. And then once we do those experiments, we look at them, we say, oh, okay, this fits with our model in that way. However, if I can show you that there's an analogy at the base level, then I can also show you there's an analogy at the next level, and at the next level, and at the next level. And that's what my book is about, is to show you how that analogy can follow all the way from the beginning, all the way to the end, to what is now starting to be an ether revolution.